want to thank Dario for asking me to give a seminar. I'm a physicist, so this topic is a topic that is very dear to me, and I hope that you will enjoy what I have to say. I joined recently Telecom ParisTech about 2 months ago. Before that, I was a postdoc at the Institute for Quantum Computing in Canada. So I've been working with quantum mechanics since before my PhD. And there are some of the things that you will hear today are very long-standing problems, and probably they will never be solved. I don't have answers. I have a lot of questions today. But it's really interesting because when you think of fantasy novels and magic, this is magic. This is the real magic that that exists in our universe. So I have. Okay, well there is a 1, 2, 3, 4, 5. Yeah, okay, you can see everything. So yeah, there are four themes, and in increasing order of weirdness. So we'll start with complementarity for about 10 minutes, then interaction-free measurements, and then the famous delayed choice quantum erasure. And finally, I will end with non-locality and non-contextuality. Non-locality, you may have heard of it. Probably non-contextuality is a bit less common amongst non-experts, but it's equally very surprising. Okay, so let's start with complementarity, the principle of complementarity. This is, again, you may have heard of this before, but this is the famous double-slit experiment. And I chose to talk about electrons and not photons because when you talk about photons, you may think, oh, yes, it's a wave, but electron is a thing, right? It's a little particle, so it gives you, it's more surprising when you hear about what happens. So just to summarize what happens in this experiment, so we have an electron that is shot towards a screen that has two slits. And if we cover one slit, then in the screen here behind the first screen, you will have that all of the electrons. And by the way, we're shooting them one by one. There's no burst of electrons that are concurrently traveling. So we shoot them one by one, and after a while, we will see that they accumulate on the screen pretty much behind the slit, which is a very classical behavior. And if we cover the other slit, we will see the same thing happening. So this is very intuitive. But then when we let the electron go through either slit or both slits, then we see something very strange, which is interference. And I want to comment on this because at first sight, especially when you talk about this with photons, you think, it's a wave, yeah, sure. So waves interfere and everything is fine. But these are single particles and they're shot one by one. Okay, so take for instance, this point here. This point here on the screen, okay, so the electron goes through the slit and then it lands on this point. So why, if we remove this slit, it doesn't go there anymore? Because I pointed here because this is a minimum in the interference pattern. So it has more paths available to reach this point. And yet, once it has the possibility to also travel to the other path, it doesn't go here anymore. And it's not that you think, oh, but maybe it's because I'm shooting many of them, they are interfering with each other. There is no interference of different electrons with each other. It's always one. And so we have this phenomenon of interference. And so once you see this, you think, okay, so let me now try to understand where did it go. So if you try to look at where it goes, so you make a measurement, then the interference pattern disappears. And there is this complementarity between knowing the path, the which path information, and interference. They cannot exist together. Either you have interference because you don't know the path, or you know the path and then you don't have interference. But I want to stress that knowing the path, it's a very subtle concept because it doesn't mean that if I put the measurement apparatus there and I don't look, then I have interference. No, it's not that you don't know. It's because this information doesn't exist in the universe. The property of the electron, of which path it followed, it doesn't have a value. And we will come back to this later about this valuedness or non-valuedness of properties. And this is a real image from an experiment that they did in Delft with electrons. And you can really see that it's truly remarkable that there are these parts here where the particles just don't go there anymore. But they did go there if they had less paths to follow. So this is the first, the first thing. So, okay. Now we can use this property to do what is called interaction-free measurement. So what happens? Well, let me say that. So now I'm plotting here, our prediction of where the electron might go. So if, in order for this interference to happen, well, the paths need to be, the electron needs to be able to follow those paths. So for instance, if you want interference to happen there, which means that the electron should never go there, the electron needs to be able to follow both paths. So if you are blocking one of the paths, then it is possible all of a sudden for the electron to go there. So what do you infer if you see a signal in that spot? You infer that there was maybe something that was blocking the paths. But what is strange here, that there is always one electron. So the electron clearly followed the other path, because this one was obstructed. But there was nothing going here. Nothing interfered. Nothing had an interaction with that object. There was nothing interacting. There was nothing physically happening, and yet the possibility, just because that possible path is not there anymore, the interference doesn't happen, and we can observe something. So this is the notion of interaction-free measurement, because we are measuring an object, and there's nothing physical interacting with it. This is also, you can explain it with the Mach-Zehnder interferometer, which I think in telecommunication is something that you might be more familiar with. But the point is that you have two possible paths which are interfering. And in this case, this is like the dark port, which is like the point in the screen where you never have a signal. And all of the signal is going out here. And now, if you block one of the possible paths, then this beam splitter is just acting randomly. So if you will see something coming out of there, then you know for sure that there was an object there. So in this case, we are able to discriminate half of the times. Half of the times we will know, 1/4 of the times we will know if there was an object, because half the times it really goes here and it really hits the object, so we see nothing. And if it goes this way, then half of the times it will come out of there. So how does this happen? I don't know. I'm just telling you what happens. So let's bring it a step further, and let's put these two things together to do what is known as the delay choice quantum erasure. So we go back to the example with the two slits. The two slits are open, and now we put filters in front of the slits. So for instance, we can filter electrons with spin up and spin down. So let's say that those who go through the upper slit have, and if they make it to the filter, they have spin up, and the ones that go to the lower slit and they make it to the filter, they have spin down. So in this case, the paths are labeled. Okay, so where is the label? The label is on the electron. So the path information exists somewhere. It exists. It's on the electron. It's on the same particle that is traveling, but it exists. And so we will not have interference. But can we erase that label after the electrons have traveled through the first screen, after they have traveled through the slits and they have been tagged? Yes, we can do it. And this concept of erasing this information is it's a bit subtle. It's not the same as scrambling information. If you scramble information classically, it's still there. It's just, you just scrambled it. So it's not about randomizing things. It's about this coherent quantum filtering. So what we can do is we can put another filter that now is compatible with both those spin directions. Okay. So, by the way, yeah, if you have questions, feel free to raise your hand and stop me at any time. So, so the key thing here is that after this third filter, we are not able to tell which slit the electron came from. That is the fundamental thing. If we can tell where it came from, not only if we cannot, if that information does not exist anymore, then we are back in business, and interference happens again. So this is quantum erasure. But now, can we try to do something a bit more clever? What if we erase those labels after the electrons have hit the screen? So we wait until the experiment is over. We don't see interference. Can we still erase those labels? And this is where the delayed choice in the wording comes from. So yes, we can do it. And let's see. So in order to do it, clearly we cannot leave the labels on the electron, because once the electron hits the screen, then it's gone. So we need to put the labels somewhere else. So we need another system, an auxiliary system, and we need to have it interact with the slits, and with electrons going to the slits. And so now the label still exists, and we don't see interference, but it's in a third system. It's in this auxiliary system that we keep. We put it aside. Yes.
Counting labels in that auxiliary system, or do something more?
So far, we are only putting the information on the auxiliary system, and we are letting it be. Just because of the fact that the information exists, we don't see interference.
But the information is a spin.
It can be another property of it depends. It can be it's yes. For instance, yes, it's a spin. If you use photons, it can be polarization, but it can be any property that you can distinguish with a measurement. Okay, and so we keep doing this procedure, and we accumulate a bunch of data here on where the electrons landed. And for each electron, we know we have its quantum system, this auxiliary system, and we keep them all in a big box. And then we make this table. So we record what screen position the electron hit, and then we have the system that contains the label. And then what we do is we do something similar to what we were doing earlier with the third filter. So we make a measurement on these systems, and this measurement needs to be unbiased with respect to the labels. So it needs to be a measurement that after I know the result of this measurement, I know nothing anymore about the labels. And since we have two labels, it's a two-dimensional kind of space. So it's a two-outcome measurement, and so we will have a string of completely random measurements. Because again, since it's unbiased, we cannot predict what it will give us. And once we know it, we don't know what it was. And we have this string, and what we do is we tally them together. So we keep all the outcomes that gave the same result of this unbiased measurement. And then we plot only those positions. And we see interference again. How did they know? How did the electrons know where to land on the screen, so that in case in the future someone measured that system in an unbiased basis? And the thing is also that there is not just one unbiased basis, there is more than one choice. How did they know where to land to make this happen? By the way, if you plot only the ones with A, you get another complementary pattern, and if you put them together, you get the two big ones. I made this by hand, so maybe now it's not so clear. But so the whole data splits into two sets, and each of which is showing interference. But the sets would be different had we chosen another measurement, but it would still work. Yeah, I don't know why. Nobody knows why it works, but it works. Okay, how is it going? Getting a feeling that this thing is a bit, yeah, what it is. Okay, so the last thing is, so I want to start with non-contextuality first, and then I want to leave non-locality for last, because non-locality for me is one of the best things. So contextuality, this is all about measuring properties of a system. So let's say we have some system, and we want to observe some property of it. And there may be many properties that we want to observe. But let's say that we pick one, it's this A, this measurement A that we want to observe. But we can choose a context for this measurement. We can choose to measure A together with another observable, A prime, or another one, A prime prime. It shouldn't matter, especially if we pick compatible measurements. So this has nothing to do with the uncertainty principle that you cannot know pairs of quantities together. No, these are all compatible quantities. It has nothing to do with the Heisenberg's principle. So the result of a measurement of A on this system should not matter, with respect to which other thing we're measuring with it. But in 1967. Cochrane and Specker proved that it does. So with a constructive proof where you show that there is a system where you essentially cannot possibly give a value to all the properties at once. Which means that either the properties of a system depend on the context, but this is crazy because anything can be context. Whether it's Monday or Tuesday, whether my shoes are tied or untied, anything is context. So this is a bit ridiculous, to have all of these properties depend on the context. But if you still want a theory that makes all of the predictions that quantum mechanics does, then it either needs to be contextual, which is crazy, or you cannot have definite values for properties. This is one of the best proofs that the values of properties of a quantum system do not actually exist until you measure them. And yet it depends how you measure them. So this is contextuality, or the fact that if you give up contextuality, which is very reasonable, then you have to have non-value definiteness. And now for the grand finale. So this is about entanglement, but you don't need to know exactly about entanglement. Those of you who know about entanglement know. Those of you who don't know probably don't want to know. But it's about correlations. And just to be clear, correlation means if two things are correlated, I can learn things about one by looking at the other. That's all we need to know about correlations. So let's say we have a source that emits these correlated particles, but they are entangled, so it's a bit more than just correlated. And we have two people, and they each of them takes one. Ooh, I'm going really fast. Each of them measures a particle, and they have this measurement device with settings. And the rule is this of this game: if the settings of the two measurement apparatuses is the same, then the outcomes of the measurement will always be opposite. So they're perfectly anti-correlated, which means maximum correlation. If the settings are completely different, then the results are random, so zero correlation. And if you have something in between, then you have some degree of correlation. Okay? So this is what we observe. Now, how do the particles know how to behave? How do they know that, let's say that the measurement settings are the same. If this particle gives one outcome, how does the other one know that it has to give the opposite? Let's make some hypotheses. Can they communicate? Yes, why not? I mean, of course. It's a perfectly reasonable hypothesis, right? This particle here goes into the apparatus, looks at the settings, and goes, hey, these settings here are such and such, and then the other one goes, okay, and it knows pretty much how to behave, even probabilistically speaking. Okay, so this seems reasonable. So how do we prove that this cannot happen? Well, we make the two measurements happen in such a quick succession that there is not enough time for light to travel, for a signal of information to travel from one particle to the other. And if we do this, the correlations are still there. So it cannot be communication. Can it be faster than light communication? Why not? Maybe there is a signal that we don't know about. I mean, these things are so strange anyways. There could be some signal that we don't know about that travels faster than light. But there is a big problem with this hypothesis, and it's that if two events are separated, we call it by a space-like interval, which means that light cannot travel fast enough between these two events, then the causal order of these events is not universal. It depends on your reference frame. So it could be that you see this, the measurement of A happening before the measurement of B. And so you think, OK, maybe there is this faster than light signal that travels from A to B. But another one of you in a different reference frame says, hey, no, wait a second. I saw B happening before A. And both of you are right. Like, it's not that one reference frame is preferred with respect to the other one. And so now you start saying that, OK, maybe then the signal travels back in time as well. And it starts to be really complicated to hold this, this hypothesis of a signal that travels faster than light. Because then you have to say that it also travels backward in time. So probably they don't communicate, backward in time. OK, what if, so yeah, this would violate causality. What if they just contain a very long list of instructions? If the settings is this is the outcome. If the setting is that, this is the outcome. And same for the other particle. With this kind of lists of instructions of how to behave when you're measured, maybe this could work. This could be a possible thing that happens. And still, maybe we don't know about these labels, these lists. And these are what are called local hidden variables. So they are local because they are contained within each system, and they are hidden variables that we don't know about, and that they actually make the system work. But this is also not possible because they violate Bell's inequality. And let me quickly summarize what it is about. So we say that the measurements have two outcomes, and we label the outcomes +1 and -1. So the settings are 0 and 1 for Bob. Typically, we call these people Alice and Bob. So for Bob, there are two measurement settings. For Alice, also there are two measurement settings. And we just write this combination, this particular combination of the outcomes. And we pick this combination because this part, B0 minus B1, is 0 if the outcomes will be equal, and this part is 0 if the outcomes will be opposite. We are talking about values in that hypothetical list of what to output given a certain measurement. So if you write this combination, then you see that the outcome can be either +2 or -2. And then if you take the average of these, if you take there are 4 terms in here, and each of them looks like this. And now if you take the average of those, which means that if you do the experiment many times, what will you observe? So each of those is essentially the probability of the two of AX being equal to BY minus the probability that they're different. Fine. This is just math. So you can replace that combination with this combination because this one you can measure. You can do an experiment to measure this one. And you see that that one has to be bounded by 2. And so you say, if there is this sort of lists, of local lists, then I cannot be able to violate this bound. And instead you can. You can pick some settings. There is a choice of settings. I'm not going into the details now of that. There are some angles that you can choose for your settings. And you can go all the way up to 2 times square root of 2. Which means that your premises were wrong. That you cannot reproduce these events. You cannot describe what happens even if you have this local hidden variables, this enormous list of how to behave. OK, this was my last slide. And I went a bit fast because I was afraid of running out of time. So we have some time for questions now. Thank you for listening to this blurb. And yeah, let's go into a bit of Q&A if there's anything you want to know.
I did not really understand this last slide.
The last slide. Yeah. OK. So, OK, we have half an hour. All right. So we are making a hypothesis that there is something in these photons, in these systems, that we don't know about, and maybe that's what makes everything work. And so one way that you can do this is operationally, and you say that the most complete description that you can have is you say there is just this list of things that say if you're going to be measured in this with this setting, output this, and in the other one there is the conveniently relative information for the other particle, and so on and so on, and you can do this for all the measurement settings. You say this might work.
This might work to explain.
To make things happen. We are trying to understand how these systems can do what they do. That is to have this behavior, to have completely anti-correlated outcomes if the settings are the same, and to have completely random outcomes if the settings are different, and that particular partial correlation if the settings are in between. So we showed that it's not because they can communicate, but maybe there is some information already in there from the beginning. And so if we take, so these 0 and 1 are possible settings. There are many, many settings. Let's call 2 settings, pick them, and call them 0 and 1. And then B0 and B1 are the 2 possible outcomes for that particular setting. So for that particular setting, since there are 2 outcomes, they can be either the same or different. There's no other option. So in this combination, either this term or that term is 0. And the other one is plus or minus 2, depending on the specific values of plus and minus 1 for A and for B. It's just a construction. It's a convenient combination of these terms that gives this number. And then, because the thing is that once you can only make one measurement on these things. You're going to make more than one measurement. So you're going to reveal only one of these quantities. But so instead of, because you can't measure all of them, then you can do an average. And if you do an average of these terms like A1B0, A1B1, A0B0, A0B1, then if you have, they're all combinations that look like this. And on average, the value of those combinations is just the difference of these 2 probabilities. So now you do that. You make many copies of this. You make many experiments. And you collect all of this data. And now you have that, if you put this together, now this thing has to be bounded by 2. And you can craft a particular system, an entangled system, that violates that inequality, which means that your premises were wrong. And this is what violating Bell's inequality means. You can also play these non-local games. So you can see it as a game between a referee and 2 players. So you can say, the CHSH game, I think it is that if, let's say, you and another player, you receive 1 challenge bit from a referee, and you win the game if your answer, if the XOR of your answer is equal to the end of my bits. You can think of it like that. And classically, you can win 75% of the time. But if you have access to an entangled state, you and the other player have access to an entangled state, then you can win 83% of the 83? 85. So you can do better than what you can do classically. There is an even better example, which is called the Ghz game. In this case, there are 3 players, and you each receive a challenge bit. And in that case, the XOR of the answers have to be the OR of the bits, I think. And in this case, you can win 100% of the time if you use a multipartite entangled state. So there is an operational advantage. It's not just, there are tasks that you can do if you have access to quantum resources that you couldn't do otherwise.
And that was precisely one of the questions. So now that we know 2 things. One, there are questions that we don't know how to answer, and the other part is that, we can cheat or have a competitive advantages. Mm-hmm. How would you use that in practice? So you were starting already answering to this question, right? So having access to entangled state
yes.
allows... So
yeah, exactly. So there are many, there's a lot of research in quantum technologies, and especially the technologies that we can develop because we know we have access to this particular phenomena that are not present in the classical world. So, for instance, one thing that we can do is we can do metrology. So the measurement of properties of systems with an incredibly higher degree of accuracy and sensitivity. For instance, essentially by using interference. Most of the times it's interference that allows to do that. Or one thing that is it's very popular now. It's quantum key distribution. So there is a way of exchanging keys to then use for cryptography, and you can phrase this as distribution of entanglement. So if you're able to distribute entangled states, then you can make measurements on those states, and since the outcomes are correlated, then it's like you are creating from nothing. You are creating this correlated data that you can use as key, and because of properties of entanglement, one of which is called monogamy, which means that if two systems are entangled with each other, they cannot be entangled with anything else. Then it's also true that no one else will have this data. So it's a very powerful primitive that we can use for cryptography. And Romano, for instance, is working on this.
Yep, so your multipartite entanglement was just pairs or pairwise entanglement between multiple parties?
No, you can have genuine multipartite entanglement, but it's not. So they're all entangled with each other. It's like a. So once an entangled system is pure, which means that it's not correlated to anything else, it's. Am I answering your question?
I don't know what is pure, so.
Okay. So you see, okay. No, you were asking how to make multipartite entanglement.
Yeah, because you were saying that in the case of multi-party entanglement, you can win some special game 100% of the time.
Yes.
And then the question was, in this multi-party entanglement, do you violate monogamy, or you just...
No. You don't violate that. It's that the state is a different state. It's a state. So once you start going up in the number of parties, then things are getting a bit more complicated because you have different classes of states, and you cannot transform one class into another. So it's truly, you have more complicated sets of entangled states. But one of these is the Ghz state, which is used for the Ghz game, which is the one that I was mentioning. And in that case, if you measure one of the states, then you destroy the entanglement everywhere. So if you have these three players, if you measure one of them, then you don't have entanglement between the other two anymore. So if you partition it in this way, then it's still monogamous in a sense. And it doesn't matter which one you measure. The other two will be non-entangled anymore. They're correlated classically, but not in a quantum way.
Question that is not directly related with your talk. Several companies are claiming that they built quantum computers, IBM, Google, Apple. You can even program a qubits computer. That this machine can be emulated by a regular computer, and I would like to know your point of view on the real state of the art on a quantum computer.
Yeah. So as you raised a very important point about simulating the physics of your processor. So the scaling of how complex it is to simulate something, it scales exponentially in the number of qubits. And at the moment, I think IBM has a 20 qubit computer. Well, he had the 5. I think it's coming up with a 21. So that is still doable. We can simulate up to 40, 50 qubits, but we cannot go beyond that. So Google now is going to come out with a 49 7x7. There's an array of qubits, and that's pretty much on the edge of what we can do. So anything beyond that, it's already impossible to simulate. But there is a big difference between not being able to simulate something and having something useful. So the first step in this race towards a useful quantum computer will be to make something that works and that we cannot simulate, but it will not be something like if you had 100 qubits, that you can definitely never simulate that. but probably you cannot do much with it. So you will need maybe thousands of qubits in order to have something useful, that fault tolerant, that can solve problems that are truly useful, like protein folding or new materials, and so on and so forth. So we are at a point where we are pretty much on the edge of what we can simulate and what we can't. So once we pass that, which will happen probably next year, because by Christmas now we are making, as I said, this 49-qubit processor. So we are on the edge of what we can simulate and what we can't. And past that, we are already in a new regime of having a machine that we cannot exactly simulate and predict what it will do. So it can give us, you can program it to solve some particular instances of some problems, but to have something programmable and useful, there will still be a lot to wait.
Okay, but if I understand what you're saying, and again, that's not my topic, I mean nothing about it.
Mm-hmm.
You're claiming that it's a fact that we can build today a quantum computing machine.
Yeah, yes, it depends what you mean by quantum computing machines. Even the 5-qubit machine is a quantum computer. Yeah.
The physics of the machine is working
absolutely,
from the quantum.
Absolutely, yes, and it's programmable, and you can do simple gates on it. We need to scale it up in order to make it useful. Yes?
Just a question about more fundamentals to what you showed. So usually for the Ghz inequality problems, they are talking about non-locality to trying to explain what happens.
Yes.
In some way. In the example before, there was a choice between either forget about the context independence or value definiteness. For the Ghz inequality, I think that there are some people proposing also to abandon value definiteness instead of talking about non-locality.
Yeah, so maybe I didn't stress this enough because.
Yeah, not a bit.
Yeah. So what are the premises here, right? So. So if you want a theory that can reproduce everything, so it either needs to be non-local, which means that it's like, because for instance, this is a theory, right? You say this is a complete theory of what I have here and what I have there, and there can be classical correlations and everything. So so if you want a theory that is able to predict what happens and describe all these phenomena, so either it has to be non-local, or it also doesn't allow value definiteness. So it is because throughout the proof we are assuming that these things have a value. So that's the other thing that may fall. But then you still need to explain how it happens. So.
I have a question that might be strange, but if you
the topic is strange.
lose an electron somewhere, you don't really know where it is, and then suddenly it interacts with something, so you say, oh, it's there.
Yes.
Automatically, you know it's not somewhere else.
Yes.
So there is information traveling there?
That's a very good question. So this is, in fact, Einstein was very bugged by this problem because so the description, when you say you lose it somewhere, what you are implying here is that there is some description that kind of says that the electron could be here, could be there. This is the wave function. So the wave function can be very spread out in space. It can have almost any shape. But at the end of the day, the particle will show up somewhere if your measurement is sharp, right? If you try to localize it, you will find it somewhere. You have it. It's one. You're going to find it, and automatically it doesn't appear somewhere else. So, yeah, the question is, was it there all the time and I didn't know it? No, because the position wasn't defined. So how does it know that it has to show up only in one place?
Exactly.
I don't know, but it's a very good question.
And so here it's a bit the same thing. You say you have two particles.
Yes,
so
here we have two
two
particles.
objects.
Yes.
And so you say one of them has information about itself, the other one does not have information about itself. But
Yes.
you could say it's one object in two places. Like the
Yeah,
object
and this is exactly, and this is a non-local theory.
I have a question. So first of all, when you wanted to invalidate the hypothesis of communication,
Yes.
you were able to measure so fast that that it could not be possible for them to communicate.
Right.
Okay. So what about if you go to the first experiment, the one, not this one, the one with sorry, the one with the electrons. With
okay.
Exactly.
Okay.
So in this experiment, apparently the interference is when they have two choices, when the electron has two choices.
Yeah, in this case, it has two choices.
Where are you able to do so to selectively close alternatively one hole and the other hole and the other hole, so that every electron has just one choice for each measurement. So in the sense that you unallow the possibility for having two contemporary choices, but at the end, will it be, so the outcome, will it be like the interference or no interference?
So let me understand. So let me just go back here. So you have the electron that goes like this.
I want to synchronize the filter or closing a hole to the generation of electrons, so that every electron can only go.
So you shoot it and then you close.
I shoot it and I close the first, then
Yes.
I shoot it and I close the second, then I shoot it and I close the first.
Yeah.
So
This is, so you will see this, because closing one means that you know the path. So if you close these two at random, you will see this sort of thing that builds up, because for each of them you know the path. And then there was a question here.
Yes. By the way, I have two questions. First one is easy, the other one is
Okay.
philosophical. First one is, it's often said that it's as if there was a communication faster than light speed. And it's often said that it's, even if it were true, it couldn't be used to communicate.
Yes.
Usefully because of the causality.
Yes.
Could you remind us why?
Yes, that's a very good point. So yeah, let me remind everyone about this very important point. So if I have these correlations that are stronger than classical correlations, can I do anything over here to influence what I have over there? Because it's very tempting to think that it is, and that you can do faster than light communication. But it's actually not possible, because when you, so there is a mathematical way of showing this, which is that when you compute the state of this system, the state of this system is independent of anything that happens to this one. They are correlated, because correlation and causation are often it's easy to confuse these things, but it's very subtle. But it's true that these two systems are only correlated. That there is no causation. That there's nothing that you can do on one of them that will influence the other. So and it's, again, you read about it more often than you would like, but yeah, it happens that some people think, oh, but I can use this to do faster than light communication, but it's actually not possible.
And I have my philosophical question.
Okay, this wasn't the philosophical one.
In the history of science, we are used to things that seem very weird, and that, for instance, the history of the heating or whatever, or even electricity and so on. And then we discover new metaphors that make things obvious. So do you think that in this case, someone may come someday with a new metaphor that says,
of course.
It's obvious, but we were just looking from the wrong angle. Or do you think that it's possible that it's beyond any human understanding? You're right. This is a very philosophical question, and I'm tempted to. It's not that it's because we tried so much and we failed so far that I'm negative about this. But it's because I think that it may be beyond our understanding, but it's mostly because even from an evolutionary point of view, we've always interacted with the classical world. We never experienced quantum effects before.
We never experienced either relativity.
That's a very good point too. But yes, that's true. We haven't experienced any. In fact, that's why relativity is also quite unintuitive and yeah.
You have to build a quantum computer in order for it to understand.
And then explain it to us.
or not.
Yeah, so I think at the end of the day, I think that this might be one of the things that we can never truly understand and figure out how it is that these things work. Because we have perfect models. We have a beautiful theory. It works perfectly. It's the best theory that we ever came up with. We tested it and tested it and tested it to so many digits of accuracy, but it's only a model. It doesn't tell you how it is possible that these things work. And that's also why we make these models that are very general, like we say local hidden variables. It can mean anything. Because we are talking about locality itself now, and we are already rolling things out one by one like this. So the way in which we approach these things is already pretty good. Like we're kind of trying to make really general statements and to talk about single concepts like locality, contextuality, and so on. And we are able to make statements about this thing. But even so, it's still escaping us the mechanism that makes these things work. There must be a mechanism of some sort. It's not that otherwise things would be random.
A very practical question. Sorry. Okay.
Just to for what you said that there must be something that explains how it works, but the quantum physics formalisms explain all what you observe. So
it models it.
It models, yeah, it models. Right. So what is the question is why do we have this model? Why are we this model for the quantum mechanics? That is the question, I think. That,
so you're saying why are things working like this and not in another way?
Yes.
Why this particular model?
We know that the model of quantum mechanics with the Hilbert space and so on, it is working. There are many experiments that show that it works like this, and so the question is how to derive this model from
yes.
that may make us understand a bit better.
Yes, indeed. In fact, there is a branch of quantum foundations where they're working on deriving the rules of quantum mechanics from simpler axioms. This is a very active field. Yeah.
But the point is that it's apparently inconsistent, because internally quantum mechanics is consistent, but it's not consistent with everything else we do in physics. So
it depends what you mean by consistent. Because the classical physics derives from like you can start from quantum physics and then derive classical physics.
No. The point that in your talk you are basing your talk on the fact that it's you have an inconsistency, then you try to find a solution which is faster than speed, but you violate causation, so you don't want, so you still have a contradiction. Then you say there must be a list of hidden variables that solves the contradiction, but only apparently, because you bump into another wall. So at the end of the day, we still live with a contradiction.
It's a contradiction between classical explanations and the quantum theory. Yes.
So it's internally consistent, but there is a global inconsistency that we would like to... efforts to find a classical theory that explains the same thing seem to have led, well, not nowhere, because we learn many things, but it seems not to work.
I have a stupid question. I'm not physicist, but suppose that you have two people, let's say Alice and Bob, which hold a rope. Very, very, very long rope of hundreds of thousands of kilometers. So if Alice pulls the rope, Bob should instantly
feel the tag, right?
The signal. If there is no elasticity, no...
but this is the...
my question, suppose it exists.
Okay.
It's an absolute... so you could carry a signal faster than speed of light. The rope is...
If you had that, then the speed of light wouldn't be the speed of light that we have. It would be the speed of the interactions in the rope.
Okay, so
the speed of light is the speed of transfer of the fastest transfer of causality. So we would have a different speed of light.
Okay. So that's why you always consider the speed of light at the theoretical bounds of... okay. Thank you.
You can even avoid putting a number on it. But you can just say there is a bound and it exists. Yeah, that was...
When you were explaining the interference, you insisted a lot in the fact that they are generated one after the other, not at the same time.
Yes.
but it's not clear for me what this is proving, because the interaction that could be in a state that includes time as part of the state.
Yes, so you're saying it could be that the electron leaves like a trace or something, and then the others are interacting with it. Is that what you mean?
It's carrying a state that includes time as a part of the state, as a variable of the state.
Yes.
And they were generated, because they are generated by the same source.
Oh, you can generate them by different sources.
And then you can imagine that there are somehow...
Yeah, you can always complicate your model and try to...
That's what I'm saying. So the fact that they are generating one after the other doesn't mean that there is no a kind of interaction.
True. It doesn't imply that there is zero interaction, that there cannot be interaction. It's just that it makes it a bit more understandable, and it already, because I get questions sometimes, oh, but maybe they are, the electric field of one is interacting with the electric field of another electron. But if you say that there is only one at a time, then you're already, removing this thought.
And there could be another field.
There could be something that we don't. Yeah, there could be something.
Talking about metaphors that you mentioned earlier, I don't know if I'm not familiar with it, so I don't know if you heard about the walking droplets and the analogies between. So, what's your? I don't know. Do you think such paths could be inspiring?
Oh, it's a
for instance, with what he said.
It's a beautiful experiment, by the way.
Like the action from distance, like what he said, like the big rock could be, I don't know, something like whenever you try to do an action here, it's the entire space that moves somewhere that makes the other thing change its state.
So just to remind the audience about this experiment, it was done here in Paris? In France, somewhere in Paris? Okay, in France. I forgot where, it was somewhere in France. And it was a beautiful experiment where they were making a surface of a liquid vibrate, and there was a droplet that was bouncing without merging with the rest of the liquid. And so they could use they could make this analogy between a wave function and this substrate. And then there is this alternative interpretation of quantum mechanics called the pilot wave theory, where you say that you have particles, but they are guided by this wave that pushes them around. And you could make this analogy with this vibrating surface and the droplet. And there are some really beautiful videos of the droplet like going through the slits and sometimes hitting the screen. And of course, you can show some of these effects, but it's because you have a wave that is interfering. So you have a medium, and you have a lot of things that are not in the quantum theory. So it's a beautiful way of making a metaphor and describing some of these effects. And if this model could explain all of the effects, then we would accept it, I think. But it can only reproduce some of them.
I have a more practical question about what are you working on exactly? Like I said, prospering question and answer to questions.
Yes. So so as I was saying, I spent the last 2.5 years at the Institute for Quantum Computing, and I was working on quantum repeaters. So going back to what I was saying about the technologies that we can come up with by exploiting these quantum effects, one of these is QKD, or distributing entanglement. And the problem with this is that you need to send quantum states, quantum systems. And quantum systems are very delicate. And one of the most promising ways and easier ways of doing things is to use optical fibers. There's the optical fiber network that we already have, and just send photons because they are easy to manipulate. You don't require vacuum. You don't require cold temperatures. We know a lot about how to produce them and so on, and to measure them. But the point is that fibers are leaky, and so if you need to make states that have a handful of photons, there is only so much distance that you can cover. And so the idea of a quantum repeater is a device that amplifies the quantum signal, but the problem is that you need to have an amplifier that doesn't measure. So it needs to amplify something that doesn't know what it is. And so the way I approach this problem, and I'm still working on it, is to use quantum error correction. So you treat loss as an error on a quantum system, and then you correct for it using these quantum error correction protocols. It's work in progress.
where time is up.
Okay.
So, I think that we can thank you.
Thank you.